Hello, calculus students. Welcome to our first week of AP review. Before I begin with Euler's method, I want to remind you to check out the documents about how to use your calculator that I've posted on Google Classroom. These are some key functions that will be useful on the AP test if it is calculator active, and also for your future calculus or math needs. So please look over the key capabilities that your calculator it can help you out with in math. Not all calculators are created equal, so some calculators are able to find a general derivative, for example, whereas others can only find the derivative at a specific point. So please look them over and see if you can use all of those different functions, and then come for office hours or message me if you need help, and I'll do my best. So with that, there is one last topic actually that I need to teach you that is new about calculus, and that is Euler's method. So this goes back to our unit on differential equations, and I specifically didn't teach this because Euler's method with differential equations is very monotonous, it's very rote, it's not essential to calculus, but it tends to always come up on the AP exam. Now, I don't know if this year will be different because of the way it's been shortened, but in previous years, Euler's method has always shown up. So I do want to prepare you for that. So what is Euler's method? So before we get into the actual formula, I want to tell you why we will use this. So up to this point, practically every differential equation that we've been presented with could be solved using separation of variables. So the problem with this is that there are exceptions to that. In fact, most first order differential equations can't be solved using separation of variables. So what do we do when we're faced with a differential equation that we can't solve? And so the answer to that question depends on what you're looking for. If you're only looking for long-term behavior, then sketching a slope field is very helpful. And we can do that without too much difficulty, even for fairly complex differential equations. The problem with sketching general solutions is that it's only really good for getting general trends in solutions and long-term behavior. And there are times when we need something more. For example, when we need to determine how a specific solution behaves or a specific value that the solution will take. So in these cases, we're going to have to use a numerical method that will allow us to approximate solutions to differential equations. So Euler's method is basically an approximation of a solution. And what we're doing in Euler's method is here's a graph, and let's say this is y of x. And what we're doing is we're taking a point on y of x, and we're going to draw a tangent line to it. And then we're going to use the tangent line approximation, and we're going to move just a tiny bit more on the tangent line and get another approximation. And we're gonna move, not that color, a tiny bit more to the right and on the tangent line, and we're gonna get another approximation. So the hope is that the more and more small steps we take, the better our general approximation is. So I'm gonna show you the formula. So this is the process of linear approximation using the derivative of a function. So linear approximation should cue us to think about tangent lines. And so what we're actually doing with Euler's method here is we're taking a starting place and we're moving a small amount. Sorry, I don't know why the iPad is being very twitchy today. So this delta x is our amount that we are moving. It's what we call a step size. And how we're going to get the function's value at the new dot, so for example, like on the blue, we had a new dot there, is by taking the original f of x sub 0 and adding onto it the slope times the step size. So what this leads us to is almost a new, basically a new tangent line. It gets us a new value of y that we're looking for. And I think this will become a little bit clearer about how to use this idea when we do an example. Okay, given the differential equation dy dx is equal to 2x with the initial point 0, 1, use Euler's method with a step size of 0.1 to approximate the value of y at x equals 0.3. So I like to organize my work by making a table, starting with the old point. So the old point, our very first starting point is 0, 1, because we're given that that's the initial point that we're making our tangent line from. So we need to draw a tangent line from this point. So first we need to know the slope here. Well, x is equal to 0. So it's just going to be 0. So our tangent line is y minus 1 equals 0 times x minus 0. Well, that's just y equals 1. This y equals 1 gives us our new point value of y. So we know our new value of y is 1, and our new value for x, we're going to move by the delta x amount. So we're adding from 0 plus the step size of 0.1. So we get 0.1 from taking our original point plus the step size, which in this case was 0.1. So this point right here becomes our old point to get the next equation for the tangent line. So we're going to use 0.1, 1 to now draw a new tangent line. So our slope here, x equals 0.1, it's going to be 2 times 0.1, which is just 0.2. So our tangent line is going to be y minus our y value of the old point is 1. Our slope is 0.2 times x minus 0.1. Now this is the tangent line. So how do we get the new point? Well, we're going to plug in for x. We know our new point is going to be now 0.2 because we've moved another step size of 0.1. So we're going to plug in 0.2 here into our tangent line, and we're going to get that y is equal to 1.02 when we do out all those calculating. So we'll get 0.2, 1.02. So we're using the tangent line of the old point to get the value at the next step size. Come on. Okay. So it wants us to approximate the value at y equals, y of 0.3. So we have to keep going until we have 0.3 comma something. And this is our y value at x equals 0.3. So we have to keep going keep doing these steps until we get to 0.3. So one more time. I'll keep using blue. Our old point now is 0.2, 1.02. So we will take the derivative at x equals 0.2 to get the slope. We will write a tangent line using our old point, so y minus 1.02 now, 0.4 times x minus 0.2. And again, to get the y value at x equals 0.3, where we have x, we're going to plug in 0.3 to get our new y value. So y is equal to, when we plug that all in, 1.06. So we can say that y of 0.3 is approximately equal to 1.06 using Euler's method. Now, if you want to check, you can actually go back to our differential equation here and attempt to solve this using a separation of variables, which we should be able to do, and see what the actual value of y is at 0.3 and see if we're close. The idea is the more steps we do with the smallest step size possible, the better our accuracy will be. Let's do one more example together, and then I will leave 2 for you to try and post the answer key. Okay, so here we have, given the differential equation, dy dx equals x squared, with the initial condition, y of 0 is equal to 1. This is telling us our first old point. Use Euler's method with a step size of 0.1 to approximate the value of y at x equals 0.2. All right, let's try it out. Okay, so our initial condition is 0, 1. Our slope that we're gonna find here, we have dy dx at x equals 0. Well, that's gonna be 0 squared, so slope is 0, so our tangent line is just y equals 1. So that means our new point is going to be step size. So remember, we're going to take this old point 0, old x value 0, and add the step size of 0.1 to it to move it along. 0.1 comma 1 using this. Okay, now we're going to take this new point as our old point. We have 0.1 comma 1. We need to find the tangent line at this point. So at x equals 0.1, that's going to get us a slope of 0.01. So we'll write out a tangent line for that y minus 1 equals 0.01 times x minus 0.1. And how are we using this to get our next point? Well, our step size, take this, add delta x, 0.2 comma something. So we're going to plug in 0.2 here for x, and we'll get out y is equal to 1.001. Now, before we do another row, remember, we want to approximate the value of y at x equals 0.2. We have x equals 0.2. We have an approximation. We are done. We don't need to keep going. Because we've only done one step, this means that this approximation might not be very good. So the smaller the step size, the more steps you take, the better it is. Okay. So quick note on number 3, this is multiple choice. Pick one as your answer. Dy dx equals x over 1 plus x over 1 plus x squared, and use the initial condition 0, 0 with the step size of 0.2. And in number 4, this is free response again. I'll let you read the question. Okay, I'm about to pause and do just a quick flash of the answers. So pause your videos if you're still working on it. Okay. And here's my work for 3 and 4. And that concludes today's video. Euler's method is something that is useful in very few situations where we do not have a calculator, we don't have any technology, we have to find the approximate solution at a specific point, and the differential equation is not separable. So your question you might have is like, how do I know to use Euler's method? And oftentimes you will be explicitly asked to use Euler's method to approximate a value. Always try to use separation of variables when possible. So here it says use Euler's method, but we could have separated this to get the value. So if it didn't say use Euler's method and it just asked for the value, use separation of variables. All right, bring questions to office hours class. I am here for you. Let me know what you need. Talk to you later. Goodbye.